In this video, we're going to talk about Newton's laws of motion. So there are three laws that are attributed to Newton. There's Newton's first law, which is sometimes also called the law of inertia. Newton's second law, which doesn't really have a name, but it goes along with the equation F equals ma. And then Newton's third law, which most people know as equal opposite reaction. Before we talk about his laws, which all deal with force, we need to know what force is. Force is the push or pull on an object as the result of one object or surface interacting with another. So when two objects interact, they are going to be, with that interaction, there's going to be forces that are being used on those objects that will create different types of motion or prevent motion. Force is a vector quantity, meaning that we do pay attention to direction. So it gives not only the value, the amount of the force, but also the direction the force is in. And all forces are going to be measured in a new unit, which we call the Newton, because these are Newton's laws. Just briefly, there are two different types of forces. There's contact forces, where there has to be physical interaction between the two objects in order for that force to be exerted. So there's applied force, which is one that we're going to deal with a lot, which is where one object is physically touching and hitting another or pulling on another. There's spring, drag, friction, and normal force, which is a newer concept that we'll get into later. There's also non-contact forces. These are forces where even though the two objects may not be touching, there is going to be a force between them. So magnetic force, even though when you think about a fridge magnet, even though the magnet is not physically touching the fridge when it's holding up a piece of paper, the paper is in between the magnet and the fridge, there is still the force that holds that magnet to the metal of the fridge. There's also electrical force. We talked about this during chemistry. It is the force that's going to be the positive and negative that is going to be attracting the protons and electrons to each other. And then, of course, there's gravitational force, which we often think of as just gravity. But gravitational force, we're going to be calling that weight. Since forces are vector, they can be combined with each other. And so the forces will also interact with one another, not just the objects. So in this case, if I have two forces that are moving in the same direction, say it's two different people pushing on one object at the same time, their forces are going to combine to create an overall net force that is larger than the two individual forces by themselves. If those forces are opposing, they will subtract from each other. So this red arrow that's going in a positive direction is actually going to reduce the negative force by that amount. So we end up with a smaller negative force. In this example, we have two forces pulling in opposite directions. So imagine this is a tug of war. If you have one group that's pulling with has like 3 people versus a group that has 6 people, the group with 6 people is going to win, but they are still going to have to counteract, and some of that force is going to be taken away by the other team. And then finally, if the forces are equal, then we have a zero net force, meaning that these are balanced. This is if you had 2 equal teams playing tug of war, and nobody would actually win because the amount of force that they are exerting and pulling away from each other is going to be equal. We call that a balanced force. So take a second and go ahead and we're going to do the same thing but using numbers. See if you can determine what the final force would be and what would its magnitude be. Alright, so you should have determined that this would be 10 to the right. Our next one would be balance because there's 5 to the left and 5 to the right, so we would have a balanced force of a 0 net force. This would be 15 to the right, negative 5 or 5 to the left, 10 to the left, and 5 in the upward direction. All right, so let's get into Newton's laws. We're going to break it down a little bit piece by piece. So Newton's first law is the law of inertia, which states that an object at rest will stay at rest and an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So let's take this first part here and talk about that first. So what this means is if an object is sitting at rest, so say you have a cup on the table, based upon the law of inertia and based upon our understanding of the world around us, that cup is just going to sit there unless something else causes it to move. So an object at rest is going to stay at rest. The same concept goes with an object in motion. If something is moving, it's going to want to stay moving, again, unless something forces it to stop. And it's going to move at the same speed and in the same direction because it has this desire to remain in that state of motion. So inertia, this is the law of inertia. Inertia, the definition of inertia is an object's resistance to change in its state of motion. Think about when you are in a car. If you're sitting in a car and somebody slams on the brakes, your body is going to jolt forward because your body wants to stay in motion. This is the whole reason why we have seat belts. Even though you don't necessarily feel like you are moving when you are sitting in the car, you are moving. So when the car stops, you have inertia and you want to keep moving. So you're going to jolt forward. There is a relationship between mass and inertia. The more mass an object has, the greater its inertia is. So again, think about if there's a really heavy object, it's going to take a lot of force to get it moving because it wants to stay at rest. Or vice versa, if there is a really heavy object that is moving, it's going to take a lot to get it to stop because it's going to want to stay in motion. But as we know, in real life, objects do not move forever. The law of inertia, the second part, this is crucial, is unless acted upon by an unbalanced force. In this case, if forces are balanced, right, we just talked about balanced forces, if they are balanced, then an object is going to stay in whatever motion it is. But in the real world, more often than not, forces are not balanced, meaning there's going to be something that's going to counteract, especially if it's motion. There's going to be something that's going to want to counteract that motion. This says balanced force is no motion, but if an object is moving at a constant speed or constant velocity, it is also going to have balanced forces. That's very crucial to understand that balanced forces can mean no motion or constant motion. The most common force that counteracts motion in our world is friction. No matter what, even if it's a super slippery patch of ice, there is going to be a little bit of friction. And so that's why we don't see objects moving forever at a constant speed, right? If you push a ball, it's going to eventually stop. And the reason it's going to stop is because there are other forces like friction that are going to counteract that motion. So that's why it's an unbalanced force, because there's always going to be a little bit of friction counteracting it. Now with friction, the rougher the surface, the more friction you're going to have versus a smooth surface. That's why it is so hard to walk on ice, because it is so slippery. Your feet can't get traction. Whereas if you're just walking on the road, you have a lot of traction because of the rough surface of the pavement. All right, let's talk about Newton's second law. Newton's second law is the law of acceleration, or net force equals mass times acceleration. What it states is that the acceleration of an object is dependent on both the net force acting on the object and the mass of the object. So net force, as we talked about, we're going to look at all the forces that are acting on the object. Depending upon how much mass the object has, is going to also be affected, and the acceleration, how quickly the object is moving, is going to affect the overall net force. Let's think of it this way. If you have two objects that are the same size, but one is getting pushed by a very strong force, you're going to see a greater acceleration than the object of the same size that's being pushed by a small force. It's going to have a low acceleration. You can think of this as, imagine a football player pushing another person versus a 2-year-old pushing a person. The football player is going to be able to push that person back really quickly, whereas the 2-year-old probably not very much at all. And then the same is true if you have an equal amount of force, so the same person pushing on two different objects, but the mass is different. The smaller mass is going to speed up a lot faster than the larger mass, because if you're using the same amount of force, a large mass is not going to move as quickly. So go ahead, pause the video using the equation F net equals mass times acceleration. See if you can fill in the rest of this table. All right, so we should have that for number 1, the acceleration would be 5 meters per second squared. For number 2, you should have had 2 meters per second squared, because we are finding that we have a net force of 20, so we're going to divide it by 2 to get the acceleration. For number 3, we have 20 divided by 4, so you're going to have an acceleration of 5. For number 4, we're going to be multiplying 4 times 15. So if a mass has 4 kilograms and it's accelerating at 15 meters per second, that means that a force of 60 newtons is pushing on that object. And then lastly, if we have a net force of 10 and an acceleration of 10, that means the mass of that object must be 1. All right, so gravity, this is the force, gravitational force, but we are going to call it weight. Gravity is the force which one massive object has on another object. So the Earth is pulling us downward towards the center with gravity. On Earth, gravity is 9.8 meters per second squared. We should remember gravity is an acceleration, whereas what we call weight is actually a force. So we have this equation, weight equals mass times gravity. So on Earth, gravity is 9.8. Mass is how much stuff an object is made of, so how many cells and atoms and all of that actually make up an object, whereas weight is dependent upon the gravitational force that the object is, depending on where the object is. So on Earth, you could have a weight of 560 newtons. But if you go to the moon, where gravity is less, your weight would actually go down to just 90 newtons. However, your size, how much stuff makes you up, will always stay the same, which is 56 kilograms. So we need to make this distinction between mass and weight. Mass is the actual stuff that makes up an object. Weight is the force of Earth pulling on that object. So here we have some different examples. Depending upon where you are, the force that the person is going to experience is going to be dependent upon the force of gravity. So in all of these situations, the person has a mass of 63.5 kilograms. On Earth, they would be 140 pounds. On the moon, they would be 23 pounds. On Jupiter, which is much larger, they'd be 355 pounds. And on the sun, which is gigantic, they would actually be 3,914 pounds. And as you can see, it's because of the difference in gravity. So gravity is our acceleration. Mass is how much of the object there is. And then weight is that force that makes up the object. Which brings us to Newton's last law, which is the action-reaction. This means that for every interaction between two objects, the magnitude of the forces on the first object is equal to that of the second object, and the direction is opposite. So if I'm pushing on the wall is pushing back on me. We see this in everyday life, where if you jump off of a canoe, when you jump up, you actually push the canoe down. So this equal and opposite is also going to play a role in the everyday interactions between different objects.